Eleven nine. How do we construct and interpret a confidence interval? So we're going to do some definitions for proportions and population so we have an idea of what's going on. But so bear with me with the definitions here as we go through this. So the population, okay, a part of the population with a particular attribute expressed as a fraction, decimal, or percentage of the whole population. That is kind of what we're talking about, is a population proportion. So it's a part over a whole. All right, for a finite population, all right, the population proportion, is the number of members in the population divided by the number of members in the population. So the number of members in the population with a particular attribute. Sorry if I didn't say that. So the number of people that like the color purple divided by the total number of people. Okay? The problem is we rarely, and I do mean rarely, can we ever ask the entire population. That's called the census. We only do that every 10 years in the United States, and even still, they really don't get to talk to everybody. So the idea is we need to take a sample, and that's where statistics is born. We want to take a sample. We want to have that be representative of the population. So, next line. In many situations, the whole population is not available. All right. In such cases, the value of the population proportion is not known. All right. So we take an estimate by taking a random sample, and we have to make sure this random sample is done correctly. All right, which we've talked about before, how to correctly take a sample. And we calculate the sample proportion and use this value as an estimate of the population proportion. So just because you sample, a little bit of Odyssey and you find out that 30% of people like the color purple, if you did a sample of 100 people, does that mean that it's going to be exactly 30%? Well, no. We've talked about before in last class, we saw simulations that would give us an idea. Well, today we're not going to have simulations. We're going to do something a little bit different. So back to the definitions. Population proportion, all right, the fraction of the population that has a certain trait or characteristic or the probability of success. It's usually denoted by P. Okay? The sample proportion, that's the fraction of the sample that has a certain characteristic, and that is usually denoted, all right, by P hat. That's not really showing up there, so let me show you what that looks like. It's a P, and it literally has like an upside down V on top of it. That's not a very good example, so let's try this one. Yeah, I guess you're getting at the idea of it. So it's a P with an upside down V on it, but we call that P hat. The statistic, which is called P hat, okay, is an estimate of P, which is the population proportion. So that 30% that you sampled of Odyssey out of 100 kids that said that they liked the color purple is an estimate, and it's your best guess, your estimate of the true population proportion of all of Odyssey that would actually like the color purple. All right, so many times, come on, let's get going, we are interested in determining a confidence interval because unfortunately that estimate is almost guaranteed to be what's not correct. All right, it's guaranteed to be wrong, maybe just a little bit off, but it's off. So we want to determine what's called the confidence interval. We did that a little bit last class based off of a simulation. All right, so sometimes we do that with a mean U based off of a sample mean X bar. And other times we're going to use a proportion P, okay? And we're going to be dealing with that today. So, turn the page, keep going on the next part, okay? So, example number 1, we have a school trying to determine the proportion of students who own cell phones. They do a survey of all juniors and find that 166 out of 236 have cell phones. They then take a sample of freshmen and find 30 out of 52 in the sample own cell phones. So, calculate the population proportion of juniors. And the reason it's called the population proportion is because they surveyed all juniors. And you want to carefully catch that. You survey all of something, you have the population proportion. So 166, so P equals 166 out of 236. That's going to work out to be 0.70. So that is the true proportion. So we can say 100% certainty that all the juniors in that school, their 70% had a cell phone. The next part, calculate the sample proportion, P hat, of freshmen who own cell phones, around the nearest hundredth. So P hat, still the same idea, it's still a part over a whole, but P hat is indicating that it is a sample. This is not all of the data, and because it is not all of the data, it is subject to being wrong. If you took a sample of 52 and somebody else took a sample of 52 people, all right, you're probably not going to get the exact same answer. So what we do is make a confidence interval, an interval that we're saying, hey, it's probably between here and here, okay? And that's our best guess as to where the true proportion of people in this fake school that have a cell phone. So to do our confidence interval, you're going to jump into this formula, p hat, plus or minus 2 times the standard deviation. Now, you've already seen this formula before, but it didn't look like this. We called it mean, right, last class, so it was the mean plus or minus 2 standard deviations. I put that in the video. Well, this is the same thing, except the mean this time is going to be your p hat. It's going to be your sample statistic. Still going to use 2 standard deviations because it's still a 95% confidence interval. And then you have the square root of p hat times 1 minus p hat, some people call that q hat, all over n. That is a formula, unfortunately, that you will need to memorize. I'm sure it won't be that hard once you've done 4 or 5 problems with this. You probably won't even think about it. You won't even write it down. So for this particular question, we had a p hat of 0.577. It does help to have the pen out. So 0.577 plus or minus 2 times the square root of 0.577 times 0.423, sorry, 0.423. And then all over the sample size 52. Now this is the formula for standard deviation of a proportion. So you do have to memorize that new part, but that is how you find the standard deviation when you have a proportion. Otherwise, in the questions from last class, the simulation, they just gave us this whole standard deviation. Somebody already computed it for us, which was nice. Not every time on the Regents do they do that, so you will need to know this. Sometimes on the Regents with the simulation, you still have to compute this. Obviously, we weren't ready last class to do it, so I couldn't have you do it. All right, so that's supposed to be a 5. Let's see if we can hit back twice. All right, let's try again. There we go. All right, so type it in the calculator. You're really fast at that. Good job. You get 0.137. You can do it all at once if you want to. Just make sure you do it correctly. All right, so if you do the plus to the minus, you're going to end up with 0.44 up to 0.714. So we can say that we're 95% confident that the true proportion of freshmen, because p hat was talking about freshmen right here, is truly between 44 and 71% that own a cell phone. That's what we're going to say they are. So I think the question was, are they the same? Something like that. Are freshmen is different? Nope, not even asking that. But they could. They could ask, is this proportion of freshmen different from the proportion of juniors who own a cell phone? And our answer, even though any fool would look at 57 and 70 and say there's clearly a difference between the two, because our confidence interval says we can have any value for the freshman, that is, from 44 up to 71.4%, it could be 70%. So we can say that, yeah, they are the same, okay? We cannot say that they are different. They could be the same is what we can say. So we can say that we have evidence the proportion of freshmen is equal to the proportion of juniors because 70% is within our interval and is inside the bounds that would occur due to random variability. Okay? And p hat can be anywhere inside the interval, but typically, and this is just, big meanies on the Regents and basically math teachers, they typically take and put that value of 0.7, see how it's really close to 0.71, to make you think, oh, but it's so close to the far right side, it's probably greater. No, that's not true. Anywhere in here, and we're going to have to say, yep, they're probably equal. So those are all the different potential questions they could ask. Let's actually jump into an actual question and do these pretty quick. Okay. Yep, that didn't work. Example 2, a doctor noticed that many female patients were vitamin D deficient. She would like to determine what proportion of her patients are deficient. She chose a random sample of 50 files of female patients and finds 43. So I'm going to stop there and I'm going to write that my p hat, because this is a sample, and notice it did not say all of her patients. If it said all of her patients, we would not need to be doing statistics. We would know the answer to the question. We would say, boom, it is this number. But we're doing a sample. So this sample should work out to be 0.86. Obviously the n value is 50, because that is your total. Assuming a 95% confidence level, determine the margin of error for this data to the nearest hundredth, and what would your 95% confidence interval be? So it's asking it slightly different than some of the other questions, but that's all right. So we need to find a 95% confidence interval, which is going to be p hat, please work, p hat plus or minus 2 times the square root of p hat 1 minus p hat all over n. So 0.86 plus or minus 2 square root of 0.86, and then 1 minus 0.86, which is 0.14, all over n, which we said was 50. You type it in the calculator, you get 0.86 or 86 hundredths, plus or minus a tenth. So our interval is anywhere from 76% all the way up to 96%. All right, so justify your response is what you should be doing. Your justification is typically your work. All right, so we have our 95% confidence interval. The answer to the question is determine the margin of error. All right, so the margin of error, again, is always the part you're multiplying, the 2 times the standard deviation. Come on, stupid thing's not working, which is 0.10. So we'll label that and call it good. All right, let's go on to example 3. George Sanchez is running for mayor of a city with a voting population of a lot of people, 250,000. George has only one opponent. Has only one opponent, has been consistently trailing in the polls with 47% of people saying they will vote for him. So George pays a polling company before the election to find out what it's going to be. The polling company finds that 206 out of 500 voters plan to vote for George. We need to construct a 95% confidence interval for the proportion of all voters who intend to vote for George. All right, so let's do that 95% confidence interval. We have to have our p hat and a pen. So p hat plus or minus 2 times the square root of p hat 1 minus p hat all over n. The p hat for this particular problem is the sample statistic, which we saw that 206 out of 500 people are going to vote for him, so that is 0.412, 41.2%. So we're going to plug in 0.412 plus or minus 2 times. Again, we're showing our work here. 1 minus 0.412 works out to be 0.588. You can leave it, as 1 minus 0.412 if you want to. There's no problem with that, and you can even type it in the calculator that way too. So that works out to be 0.412 plus or minus 0.044, which, when you add or subtract it, gives you 0.368 up to 0.456. So there is our 95% confidence interval for the proportion of all voters who will intend to vote for George, or who intend to vote for George. So does it look like George is doing okay? Well, unfortunately, it looks like George is not doing so okay because it's all below 50%. So it looks like George is going to lose, but that's not what the question is asking. We could infer that and say that it looks as though George is going to lose because it's all below 50%, therefore that's what we're seeing. So it says, can George conclude that he is losing support, gaining it, or it has remained the same? So for it to have remained the same, we would expect our 47% that we just got up here, because that's what it used to be inside our interval. And unfortunately, 47% is just above. So since 0.47 is above, it's outside the bounds of what would occur due to random variability. So George can conclude he is losing support. I'm going to write that down, and we'll talk about it again. So here we go. Since the 0.47 is very clearly above the bounds of our 95% confidence interval, it is above the bounds that would occur due to random variability. So anywhere in here would occur due to random variability of different samples. What that means, right, is that George can conclude that he is losing support. So any number in between here, and we'd say, yep, if 47 was in between these two numbers, which it's not, but if it was, we could say, yeah, it could still potentially be the same. But since it's all below, we can conclude that support has gone down. All right, let's move on to the next question. All right, so here we have New York Times. Come on, work. All right, did a nationwide poll of 1,048 randomly selected 13 to 7-year-olds. Keyword there is random. It needs to be random. They're just asking their sons and daughters. It's not. Of these teenagers, 67% of the television in their room. Give a 95% confidence interval, the nearest percent, for the proportion of all people in this age group who had a TV in their room. All right, so we're going to start off with what is p hat, where we read the rest of it. So p hat is going to be the part over the whole, and they just tell us what it is. So we really don't know what the total number of kids were, but we know that it's 0.67, 67%. And we know that n is 1,048, so that's important. It's different. All right, so our formula again, p hat plus or minus 2, and then square root of p hat times 1 minus p hat all over n. 0.67, 2 square root of 0.67. I'm going to write it as 1 minus 0.67, even though you totally could write that as 0.33. You'd be okay with that. All over 1,048. And again, you can type it right in the calculator as is. 2 times all of that. That's going to give you 0.029. Okay, which then gives you an interval from 0.641 all the way up to 0.699, almost 70%. Nice. So, let's keep reading. So now we've created our 95% confidence interval. So, with results like these, okay, what that means is we could have had results anywhere from 64.1% up to 69.9%. Okay, so it's not just guaranteed to be 67, anywhere in there because of our margin of error and the fact that we're creating a confidence interval of possible values. So the true proportion, population proportion, doesn't guarantee to have to be 67%. It can be anywhere in between here. So now they do a second poll. And in the second poll, they claim as many as 69.5% of teenagers, right, have a TV in their room, age 13 to 17, of course. Does this contradict the first poll? So 69.5. Is that within the bounds that would occur due to random variability? And the answer is yeah. It is inside this confidence interval. Therefore, it is inside the bounds that would occur due to random variability. It's still possible that it is 69.5. They do not contradict each other. So our answer, I will write that out and then explain it again. Okay, so the answer is no. It does not contradict the first poll. And the explanation, of course, has to be written out, not just the justification of your work. So we're going to say since the 0.695 is within our 95% confidence interval, because it falls in between 0.641 and 0.699, it is within the bounds that would occur due to random variability. Therefore, it's possible that it is 69.5. And like I said before, notice the number is towards the top. It could be towards the high end, towards the low end. They are intentionally going to do that. There's no way you're going to end up with 67 and the next one will be like 67.5 and it'll be still right in the middle. You'll never see that. They will always design a question where it is close to a boundary or just past the boundary. All right, so that's pretty much it. Go ahead and write your summary, do your practice problems, ask for help if you need it. Thank you.